Welcome to the lecture on DFT and FFT. In this lecture, we are going to discuss discrete Fourier transform and fast Fourier transform, commonly known as DFT and FFT. In this one, in general, these transforms are used to analyze discrete time signals in the frequency domain, which is very important in digital signal processing. In the real world application, signals are finite in length. In general, the real world signals are finite in length. Although TFT, that is discrete time Fourier transform, gives a continuous frequency spectrum, it is not suitable for digital computation. Hence, DFT is introduced here, which provides discrete frequency samples and is computationally feasible for digital systems. Now let us see the mathematical definition of DFT, that is equal to capital X of k equal to summation of small x of n into e power minus j 2 pi by n into k into n. Here small x of n represents the input signal. Capital X of k represents the frequency domain output. Capital N is the number of samples. Through this equation, we compute DFT concept. Then, using inverse DTFT, again we get the original signal, that is original discrete signal, that is small x of n equal to 1 by capital N summation of capital X of k e power j 2 pi by capital N into k n. Through this formula, we can calculate IDFT. What do you mean by fast Fourier transform? Although DFT is useful, it requires large number of calculation. To overcome this drawback, fast Fourier transform is introduced here. FFT is not a new transform, but it is an efficient algorithm to compute DFT. FFT works based on the divide and conquer approach. It decomposes a long sequence into smaller sequences, uses symmetry and periodicity properties, and then combines the results efficiently. What do you mean by radix 2 FFT condition? In radix 2 FFT, the number of samples must be a power of 2. That is, n equals to raised to m. This condition is very important. In dissemination in time FFT, that is FFT concept is calculated through two ways. One is named as DIT FFT, that is decimation in time FFT. The input sequence is divided into even indexed samples and odd indexed samples. Then smaller DFT are computed recursively and combined using Twiddle factor. This is the concept of decimation in time FFT. This slide shows the flow of DIT FFT. First, the input is splitted into even and odd sequences. Then smaller DFTs are computed. Twiddle factor multiplication is applied here, and finally the full DFT output is obtained. This is the general flow of DIT FFT concept. What do you mean by decimation in frequency? Before we discussed decimation in time, FFT. In this slide shows the concept of decimation in frequency, that is frequency through FFT logic. In decimation in frequency FFT, the frequency samples are divided instead of time samples. The input sequence remains in order, but the output appears in bit reversed order. This is the main concept of that is DIF FFT logic. Twiddle factor. What do you mean by twiddle factor? The twiddle factor is denoted as W sub n power of k. It is a complex exponential term that plays a key role in FFT computation and connects smaller DFT blocks. Here we compare DFT and FFT. DFT is a direct mathematical transform and is computationally slow. FFT is the algorithm that computes DFT very fast using fewer calculation. Both give the same output, but FFT is a preferred in practical systems. So from this one, DFT is the direct mathematical transform. FFT is an algorithm to compute DFT, not separate transform. Hope you got the idea of DFT versus FFT concept. This slide shows the application of DFT and FFT. These are widely used in spectrum analysis, image processing, speech processing, then communication systems and biomedical signal analysis. Let us now see a numerical example of DFT. Through this example, we can understand the concept of DFT logic. We substitute here the values of K and N and evaluate cosine and sine in terms to obtain the frequency components. So this is the one given example sum, that is determine the 4-point DFT of the given signal equal to, that is small x of n equal to 1, 1, 1, 1. Here capital N equal to 4. This step-by-step approach is very important for to compute the DFT logic. So here first step number 1 is to write DFT formula. Already we know the formula of DFT, that is to find the capital X of k equal to summation of small x of n e power minus j into 2 pi by n into kn, where capital N equal to 4. Already then you are given some capital N equal to 4. Substitute this value in this equation. That is 4 minus 1 equal to 3. So summation, that is our small n value from 0 to 3. Then x of n into e power minus j pi by 2 into kn. So from this formula, next we calculate x of 0. That is substitute k value equal to 0. Here k value equal to 0. Then find the value of capital X of 0. After that we calculate k equal to 1. So where we substitute x of n value equal to 0, 1, 2, 3. But here k value equal to 0. So e power 0 equal to 1. So x of 0. So this equation comes like this. That is x of 0 plus x of 1 plus x of 2 plus x of 3. So what is the value of x of 0? What is the value of x of 0? This is the x of 0 value. then x of 1, x of 2, then x of 3. So from this substitution, we can get capital X of 0 value, that is equal to 4. So next we can substitute the value of k, that is equal to 1. So through this formula, that is our DFT formula, in this DFT formula we can substitute k value equal to 1, but our n value from 0 to 3, already we know this concept. Then x of n into e power minus j term comes like this. That is cos pi by 2 into n minus j sin pi by 2 into n. Where here k value equal to 1. Here we substitute 1 into n. Here also we can substitute 1 into n, because our equation has k into n. Instead we can k value equal to 1, we can substitute k value equal to 1, then our equation comes like this. So from this one we can evaluate or calculate capital X of 1. So now you substitute n value equal to from 0 to 3, that is 0, 1, 2, 3. Once we are substituting n value 0, 1, 2, 3, at the time what is the cos pi by n by 2? In our equation consists two terms, that is cos term and sin term. In this cos term we have to substitute n value. Also in this sin term we have to substitute n value, that is cos pi by n by 2, sin pi by n by 2, where we substitute n equal to 0 at the time, n equal to 0 at the time, what is the cos 0 value equal to 1. Here what is the sin 0 value equal to 0. Similarly, we can substitute n value equal to 1 in this term. That is that time cos pi by 2. Cos pi by 2 equal to 0. Sin pi by 2 equal to 1. Similar way, we can substitute n value equal to 2 here. So 2 by 2, our term come like this, that is cos pi. What is cos pi value? Minus 1. What is sin pi value is 0. Then sin in here when here n value equal to 3. Now this term comes like this, that is cos 3 pi by 2. What is the 3 pi by 2 value equal to 0? What is sin 3 pi by 2 value equal to minus 1? Substitute all the value in this equation. That is 1 into 1 minus j power 0. That is 1 minus, this is 1 minus j into 0. This 1 comes the value of x of n. This is value of x of, there is x of 1, x of 2, x of 3, then x of 4. So this term 1 minus, there is 1 minus 0. That is here 0 minus j1. Then minus 1, 0. Then 0 minus into minus plus j1. Finally, we obtain capital X of 1 value equal to 0. Similar way, we can calculate the value x of capital X of 2 through the DFT formula. In this formula, we can substitute capital K value equal to 2. Finally, we can get like our equation, that is the summation from the small n value from 0 to 3, x of n into cos pi by n minus j sin pi by n. So in this one, we can, in this n value here, substitute the n value from 0 to 3. So from 0 to 3, what is the cos pi by n and sin pi by n value is tabulated here. From this table value, we can obtain the value of capital X of 2. What is X of 2? Finally, we get capital X of 2 equal to 0. Then we can substitute k value equal to 3. So capital X of 3 equal to, instead k we can substitute 3. So once we can substitute the k value equal to 3 in our equation, our equation term come like this. That is x of n into cos 3 pi by 2 into n minus j sin 3 pi by 2 into n. So for this, in this equation we can substitute n value from 0 to 3. So once you can substitute this value in this equation, finally we get capital X of 3 equal to 0. So now final DFT output equal to, that is capital X of k equal to that is 4 comma 0 comma 0 comma 0. This is the final answer of DFT. Let us summarize this lecture. The DFT converts discrete time signals into frequency domain. FFT computes DFT efficiently. The radix to FFT is most commonly used, and both DFT and FFT are essential tools in digital signal processing. Thank you.